question we're interested in for this problem is how much will Lake Hartwell change in level when it rains? So this is a picture of Lake Hartwell from the air, and the idea is that it rains out here in the watershed, that water runs off, and the lake level rises. So we can see over here that the drainage area that goes into the lake is much larger than the lake itself. The lake itself is actually quite large. It's 100 square miles almost, but the drainage area is much larger than that. So we have a rainfall of 3 inches, and 2 inches of that are intercepted or evaporated. 2/3, which is about a typical amount of ET, but a third of, or 1/3 of the rainfall, 1 inch of water, makes it into the lake, and that causes the water level to rise. So we can address this by first drawing a sketch of the problem. So there's the lake, and here's the watershed. There's some streams, and this is the area that drains into the lake. Okay, just a very simple conceptual model. And there's precipitation that falls. And let's see, the lake will, I'm going to kind of draw the lake looking like this. There's the lake in cross section, and there's the level in the lake. Okay, so that's our problem, and we can address this by doing a volume balance. So I'm going to draw the control volume, and let's just use this dashed line that's the watershed boundary for the control volume, and it extends around the lake like that. So we can then say that the volume into the control volume is equal to the volume out plus the change in the volume stored. That's the basic balance. And we're doing this for just one rainfall, so we can do it just in terms of the volume of the rainfall. We'll also decide that there's been no outflow, that the dam is closed, and so we'll just assume that there's no flow out of the lake, and so we can set that equal to 0. So this is kind of a worst case scenario. So the volume that goes in will be the precipitation times the area of the watershed, and the volume that goes out is 0. The volume that's stored in the lake is the area of the lake times the amount of head change. This is the change in the storage. So if the delta H is right here, that the amount that the water level changes, then the area of the lake times the delta H is the volume of storage change. And this is assuming that the bank of the walls of the sides of the lake are steep. We can get fancier and include sloping sides, but this will get us what we need to know. We just now solve for delta H, which is the change in the water level of the lake, and it equals P times the ratio of the area of the watershed to the area of the lake. And we're given that information. It's P times 22.4.